Hello and welcome to MATLAB programming for numerical computations. We are in module 3. In this module, we are covering numerical differentiation and numerical integration. In the second part of this module, we have been covering numerical integration. In the previous lecture, lecture 3.4, we saw application of trapezoidal rule and Simpson's one-third rule. In today's lecture, we are going to cover multiple applications of trapezoidal rule to find area under a curve. If you recall from the previous lecture, integration is nothing but finding area under the curve f of x between points A and B. We applied trapezoidal rule in order to calculate this area, and we found that the errors can be quite high in using a single application of trapezoidal rule. Instead, what we can do is we can divide this entire region into multiple intervals and then calculate area using trapezoidal rule for each of those intervals. Then we sum up all those areas in order to get net area using trapezoidal rule. How do we do that is as follows. For the first interval that lies between a and a plus h, the area under this region using the trapezoidal rule is given by h by 2 multiplied by f of a plus f of a plus h. The second interval goes from a plus h to a plus 2h. For this interval, our area using the trapezoidal rule is going to be h by 2 multiplied by f at a plus h plus f at a plus 2h. We keep doing that until the last interval. Once we get all these areas, our integral I is nothing but summation of all these individual areas or all these individual integrals that we have obtained using the trapezoidal rule. The step size h is nothing but b minus a divided by n. When we have n intervals, we are going to have n plus 1 points in the x-axis. How that is? If the entire zone was just one single interval, that means if we were doing a single application of trapezoidal rule, we will have 2 points a and b. If we are using two applications of the trapezoidal rule, we will have a, the midpoint, and b. That will result in two intervals, a to the midpoint and midpoint to b. So, two intervals will have 3 points on the x-axis. 3 intervals will have 4 points on the x-axis, 4 intervals will have 5 points, and so on. N intervals will have n plus 1 points on the x-axis. What we will do now is go on to MATLAB and solve this using multiple applications of the trapezoidal rule. This is one of the two methods that I will show you in today's lecture for using multiple applications of the trapezoidal rule. Let's consider the example that we had solved in the previous lecture. That was to find the integral of 2 minus x plus ln x. Okay, so let's go on to MATLAB and do this problem. What we'll do is we'll open the file that we had used in the previous lecture. That file we called this as num integral. This was to calculate the integral of 2 minus x plus ln x using a single application. What we will do is we will change this to multiple applications of trapezoidal rule. I will save this as a different file. Let's call this as, say, multi-step integral. Okay. So the problem setup a equal to 1, b equal to 2, we want to integrate this function from 1 to 2. True val is this, and let's say the number of steps n that we want to take initially, let's say it's 2, right? That's what we said we will do. Okay. So trapezoidal rule, multiple applications. And let's delete the section about Simpson's one-third rule and displaying the results. And this is what we are left with. Okay, so n is 2. For n equal to 2, our h was b minus a divided by n. So our h is b minus a divided by n, and we had used myFunInt to calculate all the functions. What we will instead do is we will again keep using myFunInt, but we want to do this for all the data points. That means for all the x values x1, x2, x3 up to xn plus 1. So let's define this x vector, x vec equal to a to b, a in steps of h to b. So this will result in an n plus 1 dimensional x vector. Okay. What we want to do is calculate the functions f at x1, f at x2 and so on. We will do this using our myFunInt. Let's open myFunInt. If we give our x vec as our x as the vector, what we see is that this will result in f evaluated at all these points. This is because this function is already vectorized. 2 minus x is going to give us a vector which is of n plus 1 size, plus log of x also is going to give us a vector of n plus 1 size. So n plus 1 size vector with added to n plus 1 size vector will give us again an n plus 1 size vector. So we don't need to make any changes to myFunInt. Okay, so we can just say f vec, the vector of function values, is nothing but myFunInt x vec, and that should be sufficient. And let me delete this part. So what let us do now is just check and verify that this indeed works. So let's run this. Okay, and let's also myFunInt at 1, myFunInt calculated at 2, and myFunInt calculated at 1.5. So these are the 3 points when we have 2 intervals. Let's check what f vec looks like. Let's type f vec. So the first guy is 1, which is here. The last guy is 0.6931, which is over here. And the middle guy is 0.9055. So this is indeed what we expect. So let's clear all CLC. Now what we have in f vec is f1, f2, f3 and so on up to fn plus 1. What we want to do now is to calculate I1, I2 and so on up to In plus 1. The way we are going to do this is we'll do this in a for loop for I equal to 1 to n. So these are the n intervals. Okay, I interval equal to zeros, because there are n intervals, zeros of size of n comma 1. Okay, the integral for the first interval, so I interval, for the ith interval, this is nothing but f1 plus f2 multiplied by h by 2. For the second interval, it's f2 plus f3 multiplied by h by 2. Third interval, f3 plus f4 multiplied by h by 2. So on. Ith interval, if it is going to be fi plus fi plus 1 divided by h by 2. So that's what we will put over here, is h by 2, sorry, multiplied by h by 2, h by 2 multiplied by f vec I plus f vec I plus 1, and I trap using the first method is going to be just the sum of all these values. So I'll just say sum I interval ERR1 equal to ABS 2 val minus I trap 1. For H equal to num2 str H error equal to ERR1, sorry, num2 str ERR1. Okay, so that's what we have. Let's save this and let's run. Hopefully it will run without giving us any errors. Okay, let's go to MATLAB command prompt and see what the results are. So the integral value is 0.8760, and for step size of 0.5 the error is 10 to the power minus 2. Okay, let's now change from n equal to 2 to n equal to 20. So by doing this, the step size is going to decrease by 1 order of magnitude. So let's run and see what happens to the error. So when we run this, by decreasing the step size by 1 order of magnitude, the error has decreased by 2 orders of magnitude. The error has gone from 10 to the power minus 2 to 10 to the power minus 4. Let's decrease the step size by 1 more order of magnitude. Let's save this and run this. What we will see is that the error will decrease by further 2 orders of magnitude. So when we divided the step size by 10, the error decreased by a factor of 100. When we divided the step size further by a factor of 10, the error further decreased by a factor of 100. If you recall what this means nothing but the method is h to the power 2 accurate. It's the second order accurate method from the point of view of global truncation error. What I will do now is to try to solve this problem using a second way, and which is going to be a more easier way from writing a MATLAB program. What we are going to do is we will just add up I1, I2, I3 and so on up to In. So you will have h by 2 multiplied by Fa plus 2 times f of a plus h, so on and so forth. So finally the result that we will get is, if we were to write Fa as F1, this guy is F2, this guy is F3 up to Fn plus 1, the result that we are going to get is I is h by 2 multiplied by F1 plus 2 times summation of all the middle guys plus 1 times Fn plus 1. It's very easy to get this formula. You can very quickly try it out and get this formula. So what we'll go and do now in MATLAB is to solve this using this direct formula. From multiple intervals using the direct formula. Okay, using the direct formula, I trap 2 is nothing but h by 2 multiplied by F1, which is nothing but f vec 1 plus 2 into summation of all the middle guys plus 2 into summation f vec 2 to f vec from 2 to n, okay, plus f vec n plus 1. Oops. Okay, that's going to be our I trap 2 using the direct method. So now what does this guy do? This guy will extract the subpart of the vector from the second to nth value, and we just want to sum it up as we have written over here and multiply that with 2 and add f1 and fn plus 1, and that will give us the desired result when we multiply it with h by 2. So display I trap 1. I will also display I trap 2 ERR2 equal to ABS true val minus I trap 2. Yeah, for h equal to this num to str ERR2 Let's save this and let's run it for n equal to 200. Okay, so as you can see from both these methods, the result is the same as we can see displayed over here, and the errors that we can see between the true val and the numerical values are also the same. Okay, so what we have done really is to calculate the calculate the integral using multiple applications of the trapezoidal rule. The first one was by calculating the integral for each of those intervals and summing that up. The second and the more efficient way, and the method that I will recommend highly, is to calculate the overall result, pre-calculate the overall result, and then code that in MATLAB as shown over here. Okay, so that is what we have primarily covered in today's lecture, and we have used that for the example of fx equal to 2 minus x plus ln x. What we also did was observe that for the trapezoidal rule, the global truncation error is h to the power 2. So it's the second order accurate method when we use multiple implementation of the trapezoidal rule. In contrast, the local truncation error was h to the power 3 for the trapezoidal rule. What you can do as a practice problem is you can solve the same example by writing a code for multiple applications of the Simpson's 1/3 rule, and you can then go ahead and verify the global truncation error and see for yourself that reducing the step size by 1 order of magnitude indeed reduces the errors by 4 orders of magnitude in the Simpson's 1/3 rule. Okay, so with that I come to the end of this lecture. In the next lecture, we are going to cover integration using two MATLAB functions, trapz and quad. So we will cover them in the next lecture. Thank you and see you in the next lecture. Goodbye.